All right, today we're going to pull back the curtain on something super fundamental in computer science, algorithm analysis. Seriously, this is the secret sauce that makes the difference between an app that flies and one that just freezes up.
I mean, you've totally felt this, right? You get a new app, and at first it's just snappy, super responsive. But then, a year goes by, you've dumped all your photos, all your messages, all your contacts into it, and suddenly, it starts to crawl. So what's going on there? It's not just your phone getting old, I promise. The real answer is a concept called scalability. And this is everything for developers. It's all about building something that doesn't just work now, but keeps working efficiently when the amount of stuff you throw at it gets bigger and bigger. You know, a truly scalable app should feel just as fast with 10 million users as it does with 10.
And at the very heart of any piece of software, you've got algorithms. Now, the easiest way to think about an algorithm is it's just a recipe, right? It's a set of steps to get something done. But here's the key. We're not just asking if the recipe makes a tasty meal, does the code actually work? We're asking a much more important question. If I have to make this dish for 100 people instead of just one, how much more time and effort is that going to take? That's the real question we're trying to answer.
Okay, so how do we actually measure how fast an algorithm is? The first thing that probably pops into your head is, well, let's just time it with a stopwatch. But, and this might surprise you, that's actually a terrible idea.
I mean, it seems so logical, doesn't it? You just run the program, start a timer, stop the timer, and bam, you've got your number. But that number, what we call wall clock time, is super misleading. In fact, it's pretty much useless for figuring out how efficient an algorithm truly is. Just think about all the things you can't possibly control. What if your computer decided to run a virus scan in the background? Well, that's going to slow things down. What about the processor? Is my fancy new laptop just way faster than your older desktop? That'll change the time. Even the programming language or the specific compiler makes a difference. It's exactly like trying to compare who has the faster cake recipe, when one person is using a microwave and the other is using an easy-bake oven. The results are meaningless. So yeah, that's why we need a much better way to do this. That whole timing thing, it's what we call experimental analysis, and it's just messy. It's tied to one specific machine at one specific moment. What we really want is theoretical analysis. This lets us look at the algorithm itself, in a vacuum. It's completely independent of the hardware, of the software, and that's what gives us a truly objective way to compare apples to apples.
So, if we're throwing the stopwatch out the window, what do we use instead? Well, we count. But we're not counting seconds, we're counting steps.
And to be clear, we don't count every single little step. That would be insane. Instead, we find what we call the basic operation. This is the one key action that really defines the work the algorithm is doing. So for something that's searching for an item, what's the main thing it's doing over and over? It's comparing things. So the question changes from how many seconds to how many comparisons.
Okay, let's make this super concrete. We're going to use a really simple algorithm. It's called sequential search. So picture this. You've got a list of names, totally jumbled up, no order whatsoever. And I tell you, hey, find the name Sarah in this list. How would you actually do it? Well, you'd probably do exactly this, right? You'd look at the first name on the list and go, nope, not Sarah. Then you'd move to the second one. Is this it? No. Then the third, then the fourth. You just go one by one, down the line until you either find Sarah or you get to the end of the list and realize she's not there. Super simple, right?
So, using our new metric, how many comparisons does that take? Well, it depends. Let's say you get super lucky and Sarah is the very first name on the list. Boom, one comparison and you're finished. That's the best case. But what about the worst case? What if Sarah's the very last name on the list? Or even worse, what if she's not on the list at all? In either of those situations, you have to check every single name. So, if there are, say, n names on the list, you have to do n comparisons.
And believe it or not, it's that worst-case scenario that computer scientists are completely obsessed with. Why? Well, because it's a guarantee. It's a promise. If you know the absolute worst it can be, you know your program will never perform worse than that, no matter what kind of data you throw at it. And for critical applications, think about financial trading or robotics or self-driving cars. You can't just hope for the best case. You absolutely have to plan for the worst.
So, this whole idea of focusing on the worst-case growth rate, it needs a language, right? A shorthand for developers to talk about it. And it has one. It's called Big O notation.
So what is Big O? Don't let the name intimidate you. It's really just a way to classify algorithms.
It describes how the number of steps an algorithm takes grows as the amount of input, we'll call that n, gets bigger. The key here is that it's not about the exact number of operations. It's about the trend. It's about the shape of the growth curve. It helps us answer that crucial question. If I double the amount of data, does the work just double, or does it quadruple, or does it get way, way worse?
And the beautiful thing about Big O is that it keeps things simple with two main rules. Rule number 1, we drop constants. So if an algorithm takes 2n steps, we don't really care about the 2. The growth is still linear, so we just call it O of n. Rule number 2, we drop the less important lower order terms. So if the runtime is something like n squared plus n, as n gets massive, that little plus n part becomes totally insignificant compared to the n squared, so we just ignore it and call the whole thing O of n squared. The whole goal is to find the single most powerful term, the one that really controls the algorithm's fate when you scale things up.
And this, right here, this table, this is why all of this matters so much. Look, for a tiny input size, like n equals 10, the differences aren't that dramatic. But watch what happens when we jump to 1,000,000 items. An O of log n algorithm barely breaks a sweat. It's about 20 operations. Okay, an O of n algorithm, a linear one, that's 1,000,000 operations. Manageable. But an O of n squared algorithm, we just jump from 1,000,000 to 1,000,000,000,000 operations. 1,000,000,000,000. And the exponential one, O of 2 to the n, forget about it. The number is so big it doesn't even make sense anymore. This is the cliff. This is the difference between an app that works and an app that is fundamentally broken.
Okay, so let's tie this all back to our simple search example and see what this means in the real world. So remember our little sequential search? We figured out that in the worst case, it took n comparisons. Now we have the language for that. We can officially say that sequential search runs in O of n time, or what we call linear time. It's a straight-line relationship. You double the data, you double the worst-case work.
And here's where the rubber meets the road. Let's say a developer is building a feature to search through 1,000,000 items. If they pick a smart O of n algorithm, the app has to do about 1,000,000 operations. Your phone can handle that in a flash. But what if they, by mistake, pick an O of n squared algorithm? Suddenly, that same app is trying to perform 1,000,000,000,000 operations. It's not just going to be slow. It's going to freeze, it's going to crash, and your users are going to delete it.
I mean, just look at that number, $1 trillion. That is the real-world cost of choosing the wrong recipe.
And it's so important to remember, this isn't something you can fix by just buying a faster computer. This performance, this growth rate, it's, as the experts say, an intrinsic property of the algorithm itself. It's baked right into the logic. A bad recipe is a bad recipe, and it doesn't matter if you have the fanciest kitchen in the world.
So, the big takeaway here is this. Understanding how algorithms scale isn't just some dusty academic thing for computer science professors. It is without a doubt the fundamental skill that makes the difference between software that people love and software that just fails. And that kind of leaves us with one final question to think about. The next time one of your apps starts to feel sluggish, think back to this. Ask yourself, what invisible algorithms are churning away under the hood right now? And what's the hidden efficiency cost that's built into the digital tools we use every single day?